Alrighty, this talk is introducing AutoML, and AutoML is a really fascinating topic area. There's certainly a lot of commercial products that sort of speak to this, and we'll dive into that, but there's also a lot of open source. So some of the history, I guess about a year and a half ago, a close friend of mine, Ben Lorica, who led the AI conference at O'Reilly and Strata Data. I've done a lot of work with Ben, still do a lot of work with Ben, and he was interested in having sort of a deep dive into AutoML, what's happening, presented to executives, like for a business crowd. So I did this talk about it to really explore it, and I did a lot of research in the area, looking through open source projects, reading just way too many papers, but also playing with the code a lot to dig in, and talking to the people who are doing a lot of this work. And I presented a few business summit talks for O'Reilly about AutoML, and those were received really well. And then my friends over at IBM Data Science Community, I also do some work there. So Will Roberts and I did an article that was more hands-on. It was more of an introduction to what's going on, especially the open source side, and really more for developers, for Python developers, whereas the work before had been kind of introducing business executives. So a lot of this is based around the article that Will and I did for the IBM Data Science Community, and I'll put in a plug there. I work for a company called Derwin, and so you can link to me there at derwinai/Paco, or I'm on Twitter a lot as Pacoid, but also I'm really involved with the data science community, so that's where I'm presenting from now. So I'm going to dig into the idea of AutoML, and just as a one-liner, can we use machine learning to help our work, improve our work in machine learning? I think that's probably the best way to describe it. I mean, there is a product called AutoML that comes out of Google, and they're very famous for that. But there's a lot of other areas, and I really want to explore the whole range of what's going on, because it speaks to really the entire workflow, the end-to-end life cycle of when you're working on machine learning projects. And I'll say that you probably have a gradient problem, because almost all of what we do with machine learning is about some kind of differentiable data. You've got data, and your hypothesis is that we can divide the data into different cases. We can put labels on those cases, or we can find other ways to say that certain groups of data are interesting together. So we'll explore through some of that. But first, I want to just dive into what is a machine learning algorithm. And so if we talk about kind of in the simple case, the most common case would be supervised learning. And with supervised learning, we've got a bunch of data. We train a model. We've got labels on the different kinds of classes of data that we're interested in. The model learns those patterns. And then when you give it new data, it's able to predict or classify what labels it thinks based on what the input is. And pretty much when you look across the board at all the different kinds of supervised learning, they have certain things in common. There's little parts of the algorithms that are called learners, and those are what really track the patterns that we're trying to learn and generalize from them. And we're trying to optimize the learners by running the machine learning algorithm. And to do that, there's a couple, like from a mathematical view, there's typically a loss function, which says, hey, I can see this pattern, and I can kind of fuzz it a little bit and then generalize. So if I see something close to that pattern before, I can pick it up. And there's also usually a regularization term, which says don't overfit. And what that means is, if I train a model off of some historical data, and it learns those patterns really, really well, then maybe it will learn them too well and will overfit, as we say, such that when it gets new patterns in the future, it won't be able to recognize them. So a regularization term is a way of kind of injecting some noise so that it can be general purpose, or more general, I should say. And the way that these kind of algorithms usually work is there's typically some kind of problem, usually solved by a variation of gradient descent. Stochastic gradient descent is one way that's very popular. There's some others, there's gradient ascent, etc. But at the end of the day, you're trying to search through a haystack to find the needles. And you probably have to go up and down some hills to do that. That's gradient descent. So if I were to pick a really super well-known problem, there's this thing called the iris data set. And there's 3 species of iris flower. There's setosa, versicolor, and virginica. And this was studied thoroughly, like last century. There's this data set that's been around for decades, and it has about 150 line item or rows in it. And there are these 3 species that are described, and there's measurements for like the petal widths. Somebody got out there and like measured all these flowers and marked down the data. But we use it in machine learning a lot because it's a pretty good representative small data set that shows off a lot of the problems. Turns out that versicolor and virginica species of iris, they kind of overlap. They're very similar. And so the data points actually overlap. So a lot of machine learning algorithms kind of mess that up. Whereas like setosa is really easy to pick out. Now, if I were to take the iris data set and run it through a machine learning algorithm, say, I run it through random forest, and I'm building up a bunch of learners, each of which are decision trees. So what that means is I'm going to pick some parameter from my model, maybe 10. It says that I'm going to go create 10 decision trees. And for each one of those, I'm going to sample out of my data set, and I'm going to build a decision tree that describes how to recognize a species of iris flower. And then I'm going to go repeat that over and over. So the learners would be a decision tree, and the loss function, there's a bunch of math, but it's pretty well known. The regularization term, there's even more math. It's also pretty well known. At the end of the day, if you use an algorithm like random forest, it's nice in the sense that it has a built-in measurement of out-of-band error. So as soon as you're done training the algorithm, you already have some evaluation of how well it did. And so I did a graph there, and you can see this chart where the loss term is decreasing. Basically, as you train it and get more trees in there, the algorithm, the model becomes more and more effective at recognizing, has less error. There's a notebook. I can show it a little bit later, but there's a notebook if you want to run through where I generated all this. It uses the iris data set, and it shows using scikit-learn to train models and then evaluate those models. Now, the other thing that we really should talk about in terms of machine learning is you've probably heard the terms parameters and hyperparameters. The idea of parameters is that when I'm using the algorithm to train some learners, and I'm differentiating my data, pulling it apart, then I keep track of basically the paths that have gone through the data and how to run that again. And those are my parameters. That means I can sort of rerun the model with new data. And often that's a very large number of parameters. If you look at some of the natural language work that's being done, like BERT and the transformers, that can be billions of parameters. Hyperparameters are really interesting, though, because they are just typically a much smaller set that you use to guide the algorithms, guide the search to find the models. So if we apply this to our iris data set, then I've got 3 species, I've got 150 rows. Let's say that I want to train it with random forest and I want to use 10 trees. My hyperparameter there's just one of them. It's the number of trees, which I'll set to 10. And then the parameters that get generated when I train the model, that's going to be, 10 trees. And then for each tree, it's going to be log of the number of dimensions, so log 4. And so that works out to being over 6. Let's say it's 7. It's a pretty small model. But there's a big difference between having one hyperparameter and then 7 parameters. And the difference is that the hyperparameters really guide this search through your gradient, through all of your data. And so I want to underscore how that's a real theme here, because let's take a kind of a grand tour from a high level of machine learning. There's supervised learning, which is most of what people talk about, and that's what we were just showing. I have a bunch of data, I train a model, and I associate some labels. And then when I have new input data that comes in, I can predict what those labels are. There's also unsupervised learning, and you don't have any labels there, But what happens is the algorithms go ahead and divide up the data into, say, clusters. So clustering algorithms are kind of unsupervised. And so basically they're generating some kind of proxy for labels. But they're still doing a lot of the same kind of work under the hood in terms of differentiating data, working through those gradients. There's also active learning, if you've heard. It's a really exciting area. It's sometimes called human in the loop. And that's where it's much like supervised learning, where you've got an algorithm that's trying to train. The problem is, though, sometimes the results coming out of the model are going to have a lot of uncertainty. And in that case, with active learning, the algorithm will kick it back to a human expert and say, hey, I don't know what I'm doing. Can you give me a label? And so then the human gives a new label, a new judgment, and that feeds back in, and you iterate and train and produce better models that way. Active learning is a really interesting way, if you don't have a lot of labels, to get your people involved and really bring in that human expertise into cleaning up your data. There's also something called self-supervision. You might have seen talks out of Facebook and other companies that are using this a lot. And basically, if you have a data object, we were just talking about data classes, if you have some sort of data object, can you take different views of it? Can you take from one complex object, can you sample different views and then use those effectively to kind of stand in place of what you would do with labels? And then it's pretty much the same as what you're doing with supervised learning above. Of course, there's a lot of talk about deep learning. Deep learning is typically, what we're talking about with deep learning is a kind of supervised learning. You have different layers of neural networks, and then they're connected by autoencoders. For what it's worth, starting in 1984, I began working in this area called neural networks, and I ended up doing like 7 years of research and development in neural networks. And at the time, everybody was trying to coach me and say, hey, this will never go anywhere. Why are you wasting time on it? So it's kind of fun to see how neural networks have turned around 30 years later. But a lot of really interesting work in deep learning. Reinforcement learning is a kind of an older area of control theory, but it's being revisited in the context of machine learning now. So, I mean, you can go back like 50 years or more, and there's great stuff about reinforcement learning. They were doing control systems like flying aircraft. But now you can take a lot of those same simulations and then put agents on which learn how to navigate within inside of an environment, a simulation. And you can use deep learning to help those agents learn. And that's what reinforcement learning typically does. For what it's worth, one of my colleagues and friends and co-conspirators is named Dean Wampler. He, I believe, has spoken at Chippy a few times before. We just came out with a reinforcement learning tutorial on the Anyscale blog a little bit earlier today, which is really geared at Python developers. So I'll give a link about that later. There's also something called weak supervision, which is a way of basically, if you have a bunch of different experts that are giving you labels to describe your data, can you come up with models to describe your different experts? So maybe Joe is good at like 80% of the cases he gets right, 20% usually gets them wrong. And then Mary is really good at like a different, 95%, and it's not exactly the same as Joe. So if you put them together and you have models about where they're good and where they're typically wrong, you can start to make decisions about the experts who are labeling your data. And so then you can start to inject some machine learning into like the early stages of how you collect and label your data. There's also transfer learning, which is basically learn a supervised learning model, but then like for a neural network, keep the top layers, keep the bottom layers as they were originally trained, and let the top few layers float, and then retrain it on a smaller set of your own data, so you can reuse somebody else's model. There's some other areas too. Knowledge graph is kind of different than machine learning typically, but it's very complementary. I do a lot of work in that area. The main takeaway though out of all this is that there's a larger category called meta learning, and it's still very much an active research area. But a lot of what we're going to talk about is meta learning throughout the rest of this discussion. And so the idea with meta learning is, as we're working in Python to build out machine learning workflows, whether we're working with PyTorch, like Joel was talking about, I really love PyTorch, or scikit-learn, or whatever, as we build a workflow, what's really interesting is, can we keep track of different workflows that we've done in the past? And if you're on a data science team, can you keep a kind of history, like a database or a knowledge graph to describe problems that your team has worked on before? And then can you do some data mining off of that, so that when you have new problems your team must solve in the future, can you sort of pick up from a known point and reuse some other configurations? And so that's kind of the gist of meta learning. And it's a way of basically using data and data mining and machine learning to help make this whole process of data science much easier to work on, much more effective. All right, so let me switch gears and say, okay, we're working with gradients, and what you have in machine learning, it's probably a search problem. And it's interesting because I love Joel's book. I read that a couple nights ago, and cover to cover, and I really, really love it. And he has some similar notions there. I highly recommend buying this book, by the way, because it teaches you a sort of a grand tour of computer science theory and software engineering practice, all in like 10 scenarios, really succinct. But he goes into some cases which are basically saying, this is kind of the problem is a matter of search. And definitely, if you roll the clock back and go to like hard AI in the 1960s, 1970s, 1980s, if you look at the earlier research about AI, they were really focused on search problems. So it's probably not too strange that like the two big AI firms to pop out of Stanford, which had a lot of this early AI research, were Yahoo and Google were big search engines. When we're building machine learning models, the challenge is to be able to find the best hyperparameters for a given kind of use case for a given set of input data. And once we have those hyperparameters, then we're pretty much guaranteed that we can crunch the numbers and get to a model. So if we could just find the right hyperparameters quickly, then we'd have to do much less training, much less search, if you will. But that's not a simple task, because when we're developing machine learning models, sometimes there's a lot of challenging and even conflicting processes going on. Like, for instance, what algorithm should we use? What's going to fit really well with the use case? How much training data do we need? Do we have enough? Do we need to add more? Which features do we need to highlight? Because frankly, some features are noise. Some features are even worse than noise and have to be sort of redacted out of the data to be able to train a good model. And then once we've got models, how can we compare them and evaluate the results and understand their relative trade-offs? Because it's not simple to just evaluate a bunch of different kinds of machine learning algorithms. They produce different kinds of results, different kinds of metrics. On and on and on. There's a lot of different assumptions that when you really get into the practice of deploying machine learning and what's definitely being called ML ops, of putting machine learning into operations, there's a lot of issues to be concerned with. And also, there's always human decisions that go into the mix. Even if you have something that's been collected by machines, a big data set that was automatically collected, some human decisions went into deciding what to collect. So there's always this level of like human judgment that comes in, and we have to be able to understand it and troubleshoot it. And the other thing I really underscore is like this area of data science, machine learning, and AI, it's become so big and so diverse and complex. Really, no one person can understand all of it and really do justice to trying to solve a problem. So I really try to say that data science is a team sport. And you really have to put together a lot of different perspectives when you want to build robust solutions. And that's another reason why machine learning is a kind of search problem, because you have to be able to blend those different perspectives together. Okay, so now here's sort of a thought exercise. Imagine if you could take a look at all the possible variations of input data, all the possible gradients, and then compare out of those which would be all the possible variations of machine learning models, the optimized parameters. Okay, that would be an enormous space. It would, it would be uncomputable because it would be so large. But if you were able to look at that as the main problem we're trying to solve, then you can see, finding the needle in the haystack, basically machine learning is a search problem. So the goals of AutoML as a search problem is you want to find the appropriate hyperparameters that converge down to an optimal, semi-optimal solution after training. And you want to identify features and data transformations that produce good training data going in. And you also want to be able to learn from history. You want to be able to reuse results you've had in the past. It may be that your data is changing over time and you have to retrain models, which is typically the case. So you want to be able to bring in that kind of history and feedback as well. And there's other considerations in machine learning that make it much more complex. I highly recommend these two papers. One is called Show Your Work, and the other is called Energy and Policy Considerations. And Show Your Work is interesting because, well, actually, both these papers, they address a phenomena that's been happening over the past couple of years, almost 3 years now, in machine learning. And that's where we're seeing these enormous models, like with transformers, where you have billions of parameters. And one of the problems is that using more old school approaches to machine learning and coming up with smaller models may actually be a better solution for your customer in some cases. Time to market is really important when you're talking about doing commercial work. So Show Your Work is interesting because it actually shows cases where using a simpler, older kind of model is much more effective, even has better performance than using the latest and greatest coming from research. Energy and policy considerations is interesting because when you look at the transformer models that are being used for natural language, if you look at BERT being trained with neural architecture search, one model has a carbon footprint of running 5 automobiles for their entire lifetime, 5 gasoline automobiles. So it's this crazy amount of energy that goes into training these huge models and a crazy amount of carbon that's going up into the atmosphere. So there are energy and policy considerations, and we should be understanding how to use AI, but not boil the oceans. And I mean, like literally, not boil the ocean. There's also other issues in terms of AI trust, and certainly there's a couple of great projects. I'll call out to my colleague, Tricia Mahoney, and others working in that area with AIF 360 that's been moved into Linux Foundation, and it's an open source Python library for algorithms that can detect fairness and bias problems with your training data, and also with how your models have been trained. And good news is this is recently, part of it's been migrated into scikit-learn. So there's some great integration with scikit-learn now. And when you're working with machine learning, it's not a simple question in terms of what your goals are. You might say that you want to have really accurate models, but to a machine learning person, if you say accuracy, that can mean several things. I could come up with 4 or 5 different, whether I'm talking about perplexity or specificity or recall or precision or on and on. There's a lot of things that are conflicting. And there's also issues of like cost versus time. And, can the auditors come in and understand what the model's doing? So will I be able to pass compliance? Are there security risks? Are there privacy issues, et cetera? So machine learning can be very difficult in practice. Which is why we're really interested in being able to use computing to be able to help out with some of the more difficult areas. And that's where AutoML comes in, and it's really super exciting. If we talk about the whole workflow, again, I really want to focus on this idea of data science teams and workflows and the whole life cycle of building machine learning. By the way, there was a really great track we did last year at OSCON, the open source conference, where a lot of different companies came together and showed what are their ML ops practices. So I've got a link to it there from OPSCON. And kind of riffing off of what we were talking about at OSCON, if we have like an idealized machine learning end-to-end lifecycle, so we've got these steps that we typically go through. There's usually some sort of data preparation, and the idea is in data science, our teams spend 80% of their time doing data preparation, and it really makes sense. It's actually very true. That's the hard part of the problem. But then you get into what kind of features do you need to have that go into training your models. The feature engineering is also a really difficult part. A lot of the math, even the statistics involved in feature engineering, they're kind of counterintuitive. And even people who do statistics all day, when they're confronted with some of the work in feature engineering, they're a bit baffled by it. So not an easy part. There's also the optimization of models, the training the models. And then there's model selection. Basically, what kind of algorithm do you want to use? And if we try, 6 different kinds of algorithms, what do the results look like? How can we pick the best ones for our use case? And then once we've got models trained and we've selected the good ones, how can we really deploy that or integrate it out with a use case? If we're talking about deploying machine learning models on some sort of embedded device like a smartphone, then we may need to do some kind of model compression or distillation or other techniques. If we're talking about deploying it in terms of web services and having it, be a SaaS product, then we're talking about deploying to a cloud cluster, running in the cloud probably. So, how do we do that? And the thing I really want to point out here, one of the really big insights about AutoML is that there are related work in both data governance and also in ML ops. So what we've seen over the past couple of years is this really big resurgence in data governance ever since 2018 and what happened with Facebook and others. Data governance practices tend to provide the kind of metadata that you need to really make use of AutoML. And so that's a good thing. Both these practices are sort of emerging at the same time. They're able to work off each other. And we're also seeing ML ops, or you might want to call it different names, but things like ML ops also emerging in the same time frame. And it turns out that the data governance practices follow from your ML ops practices, right? And so you get these 3 things that sort of build on each other: data governance, ML ops, and AutoML. And they're all evolving, and they're definitely not a done deal. There's a lot of work that needs to be done in data governance, even though it's decades old. But as these are evolving together, working toward the kind of solutions we face today, I believe that the 3 will be working together, sort of 3 pillars that you stand on. So one of the other things that I've done in the past year or so is put together, this is a Google spreadsheet that's open. It's got listings of different vendors working in AutoML and also different open source projects. It's looking at a whole bunch of them. And whenever I find new ones, I just sort of toss them in there. So if you want a whole big listing of AutoML projects, it's definitely kind of one-stop shopping. The other thing is that I highly recommend this resource on GitHub. It's called Awesome AutoML Papers, and it's updated about every week. The author is doing this really fantastic job of having a taxonomy of different AutoML projects on GitHub and different papers and being able to classify them. So that's another really good place to look to find out what's going on. Okay, so I had a diagram earlier, you see at the top, of like the full end-to-end lifecycle of preparing machine learning to go out into customer use cases. So let's take the first stage, data preparation. And there are things there that you can do that are really interesting. I talked about weak supervision before, and that's where you can take the different judgments being done by people or experts and sort of treat them as a kind of machine learning modeling. There's a way to extend that that's being called auto data preparation. And if you look at projects like Snorkel or HoloClean, I think especially HoloClean I've got linked out to there. And it's really fascinating how we can start to automate some of those kinds of practices, particularly when you take into account that data science teams, again, spend so much of their time at this stage. Now, when we get to the feature engineering part, this is really difficult. I highly recommend a couple of friends of mine, Alice Sheng and Amanda Kasari. They did a book,
Hey, Paco, I think we might have lost your mic. I can't hear you right now. All right, excuse us, everybody. We're I think you might be muted.
Oh, Test, test. Is that better?
Yeah, we can hear you now.
Okay, sorry about that. There might have been a control that muted it automatically.
Yeah, no worries.
How far back?
I think it was like the last 30 seconds to a minute.
Okay, cool. So I was showing here, clicking from slide. Data prep, I think we got through that. Basically, I really recommend HoloClean as one of the really interesting open source projects right now, based off of some of the ideas coming out of Snorkel for this auto data preparation. And then feature engineering, there's a great book by Ellis Shang and Amanda Kasari that goes into just the full range of what's going on in feature engineering. Some of that can be very difficult, gets pretty heavy on statistics, but again, if we can help automate parts of it with tools like MLBox or AutoML Toolkit. There's a really great paper too, a friend of mine out of U Manchester wrote on stability of feature selection algorithms. We're starting to understand that sometimes some of the data that you feed into your machine learning models, over time, some of it is probably less risky than others if you want to have some sort of robust modeling. That paper was a very surprising one. I think it actually surprised the authors how popular it became. There's the area of training machine learning models, and when people talk about machine learning, they usually kind of rush toward this. Actually, this is probably the least interesting part of the workflow because it's pretty well known. But the hyperparameter optimization is really what started AutoML. And so a lot of the early descriptions about AutoML really focus just on this. It's sometimes abbreviated as HPO, hyperparameter optimization. And so there are some very long established projects like HyperOp. There's also AutoKeras and some newer stuff like Raytune that focus on how can we get to the right hyperparameters. And that's important. And certainly if you're working with deep learning and you're running on a big cluster, that can represent a lot of the costs that you're going to spend over time. But I do want to underscore that, like, throughout the whole end-to-end life cycle of machine learning, there are other parts of it that are probably even more complicated than this. Okay, so once you've gotten a machine learning model trained, and maybe you're using a few different algorithms and comparing them against each other, doing a bake-off, how can you help to be able to evaluate which one's better for the use case? There are projects like AutoScikit-Learn, which this gets into maybe you want to use multiple models together. Maybe you want to be building ensembles. And that was one of the big learnings out of the Netflix prize years and years ago, was the teams that coalesced together and built these big ensembles were the ones that won. So this is a really interesting area because that's a hard problem, but being able to use ensembles really, it helps reduce a lot of the risks and bias. And it's very powerful approach, sophisticated approach to machine learning. And then finally, when you get down to the point of deployment, how do you make your machine learning models fit your use case? And there are some great examples, that commercial examples like working with SageMaker, working with Watson Studio. There's native, Knative, however you want to pronounce that. But if you want to consider the idea of auto-scaling and really how do you take your models and make them fit the use case, those are good examples for it. On the other flip side of the coin, though, is where we have machine learning models that we want to embed. And I think in particular, there's really fascinating work in what's being called TinyML. So if you haven't seen it, Pete Warden from TensorFlow and the work that he's done with TinyML. Also, there's a conference called TinyML Summit. But definitely check out some of these links I have about the low power machine learning. It's really fascinating. There's chips that you can buy that cost less than 50 cents on eBay, even less if you buy them in quantity. And you can run multiple deep learning models on them in parallel and like run off of ambient light with no battery. Really, really crazy stuff. But I think that that's a lot of the future on the edge of how do we deploy really sophisticated models out to low power kinds of use cases. This talk is being sponsored, being done with IBM, and I'll throw in, I'm really not the person to speak to this, but IBM has some products in this area. There is a trial of Watson Studio. There's a link down here, IBM Biz. And if you want to go through and learn more about that, definitely we've got some people who can help answer questions. And then looking ahead, I think this is really interesting. I described before about meta learning as being this thing that's over the entire workflow and sort of learning from your history, your team's history. And that's kind of striking toward, I guess you'd say, semi-automated data science. There are a couple of projects that are trying to strike toward that. One of them is called Lale. It's in Python, and I'll show that in a bit. There's another one called Teapot that's a little bit more established. But I also have a survey here of a few different papers. Peter Bill at Berkeley, of course, has been pretty famous in this area. It is active research, but it's really super fascinating. And I think that some of the lessons learned from companies like Lyft and Uber over the past few years since GDPR was introduced, they're getting a lot more interested in this area. There's also some related things in terms of program synthesis. So if you haven't seen it, there's a great project called AutoPandas. I've got a link here. And it's a way of being able to show a pandas data frame, sort of your input, and then what you need for your training your machine learning model. And then AutoPandas can generate the Python code in between it. And there's related projects like that for SQL. But this area of like program synthesis and using machine learning, especially deep learning, to do it, I think there's a lot going on there. Definitely watch that space closely. And related, of course, there's also the auto-completion tools that are going into IDEs. And so you see things like Tab9, where they can do really smart completion for you while you're typing code. This is related. I mean, this is part of how we build machine learning models. If your IDE can predict what you need to be coding next. And then, you know, one thing that maybe it's a little bit cynical, but I think it's really true for what's going on in this. There's a great this link here: 100x increase in cloud-based computation. It's a talk by Jeff Dean from Google, and he gave this talk at TensorFlow Dev Summit a couple of years ago. And what he said was basically, look, your problem is you've got to hire AI experts, you've got a bunch of data, and you have to do some cloud computing. And you put these all together and you come out with an AI product. Well, if you can't hire enough of the right people, then you could just spend maybe 100 times more on the cloud compute, and we'll use AutoML to like replace the people you can't hire. It's kind of cynical. It's also kind of true. And so we see this from the cloud providers. They typically have really good AI teams, and almost all of them are producing some type of AutoML services to really augment your team. It's not necessarily about replacing people. It's more about, hey, as a data science team, you get really busy. You need to have some services that augment and make your life better, you know, so you can be more effective in what you're doing. The other thing is just hardware is going crazy, especially when it comes to deep learning and other areas of machine learning. If you haven't seen Cerebras and some of the others, I mean, we're talking about like 5 orders of magnitude on chip performance increase over the most sophisticated GPUs coming out of NVIDIA. So hardware is going to be one of the real big game changers in this area for making AutoML, which is expensive, something that's less expensive to use. So in conclusion, there's a lot of opportunities, a lot of really interesting work in AutoML. It's not magic. It's something that chews up a lot of compute cycles, but it can help augment the work that you're doing currently and help augment your teams. And we definitely think that as we see, you know, more of the theory advance, more of the hardware acceleration advance, this is going to become more and more of what we're doing. So we're using machine learning in clever ways to try to make machine learning more effective. That's kind of the promise. Okay, I've got some coding examples. If you have time, I can run through, or I can at least show some of the notebooks if you want to run through this yourself. Ali, do we have time?
Yeah, please take all the time you need. Like, would love to see like these examples of this. Like, this is fascinating.
Okay, cool. I'm super excited about it. I'm glad you like it. There's a lot going on here. Let me get back to first one. Well, I'll do this one. Yeah, okay, I'll do this one first. I had shown a little bit earlier about Iris. It's an extremely well-known data set. And if you haven't done any machine learning before, it's really great to have a common data set and try to work through different libraries with it, because then you know what to expect. You can kind of understand what to anticipate and see if you got the code right or if the library is working correctly. Sometimes they don't. But here's what I was using in the first few slides to take Iris and then run it through like some visualization. And you can see the clusters sort of work, like one species is really separate, but the others overlap. That's the problem. And here's some really simple code in scikit-learn, where I'm taking, doing model selection, and then going in and using random forest to build a classifier. And then I just, I take and I show the scores, the loss. Basically, as we're doing gradient descent, training this algorithm, or training the learners through this algorithm, you can see how the loss decreases. So if you want to work with Iris, that's a good one. I do a lot of work on a project called Ray, which is, like I say, I think Dean Wampler has talked about that before. But Ray is in Python. It's a way of doing both actor pattern as well as parallel task. So there's two kinds of parallelization that you can do with Ray just by adding a few decorators. And I've taken existing Python code that was fairly complex for large production systems, and after adding about 5 lines of Ray, I had parallelized it. So really check out Ray. In particular, though, there's a lot of support. It was built to support machine learning. And
Paco, do you mind making the notebook just a little bit bigger? Sorry to interrupt.
Oh, yeah. Probably too small of fonts. Let me, come on. Let me get my view a little higher, zoom in. Yeah, my system's taking a little time. Let me zoom in a little bit more. How's that? Is that better?
Can we go just to maybe 1 or 2 more?
Yeah, I'm trying to, my notebook seems to, that process is, there we go. Okay, 400%, okay, awesome. Is that good?
Yeah, I think that's better, thank you.
Sure. This is scrolling a little bit slowly. I've got a lot of stuff running on my laptop here, so it's probably going slow. And it's probably still zooming. Let me try to manage that. Oh, come on. Okay, so what I've got here is just, it's a really brief view of using Ray. There's a part called Tune. You can see that, come on. I may need to stop some stuff. I'm getting a lot of lag here, so it's still. Yeah,
we can wait for your computer to catch up. That's okay.
Okay, sorry about that. It's like a 2-year-old laptop, and my keyboard's almost falling apart. But that's one of the biggest problems I've had during the pandemic is the local Apple store still isn't really running at full speed. Let me see what else I can do. Let me shift. No, I shouldn't do that. I want to be able to show this stuff. I can talk through it. Okay. Wow, this is not really responding at all. Let me do one thing. I'm going to turn off OBS, which is kind of what Joel was warning me about. So let me turn off OBS. My video is going to be gone for a sec.
Okay.
And once I do that, camera mic, yes. Okay, cool. Can you see my camera?
We don't have the max headroom effect, but it looks we can see you.
Okay, great. So I'm hoping that with OBS gone, which is exactly what Joel was saying, hopefully with OBS not running in the background, I'll be able to get something responsive out of my browser now. Ray is, again, this project for doing parallel processing in Python. It's very simple to use. There's a part of it that's called Tune that provides AutoML features. And so what it can do is, I'll show a quick example here. I just do a few imports to be able to bring in Ray and RayTune. And then I'm going to create something that looks a little bit like a machine learning problem. I've got this one function defined, easy objective, and I've got a couple of terms in there. I basically got a loss function, which would be similar to like what happens inside of a machine learning algorithm. Got a couple of parameters there, and basically when you get close to those parameters, then the model will come back and report less error. I'm also throwing in a few sleeps to make this more expensive, so that when it's a kind of an iterative problem, and if the sleeps are in there, then the iterations are going to cost some time. So to run Ray, I'm just going to make sure I'm not running it before. I do a Ray shutdown, and then I immediately do an init. and then that'll run a local cluster. If I wanted to run it in the cloud, I would just attach to a cluster using a very similar line, but just with an address for the cluster. And Ray will come back and tell me a little bit of something that looks a lot like JSON, but isn't exactly. It'll tell me where the cluster is running. Great, so I've got Ray running in the background. And then I'm going to come in here, I'm going to describe a problem, an AutoML problem. I'm going to say, I want to do hyperparameter optimization. I want to do a Bayesian optimization search. And I've got this metric that I'm going to try to optimize, mean loss. And remember, that's the thing that's described up here in this easy objective function. I've got a couple of arguments that are coming into it. And well, I actually need to provide a couple of arguments for Ray. So outside of what I defined, we're talking about UCB, which is upper confidence bound. If you look through the documentation about Ray-Tune, we'll go into more details about that. That's one of the kind of algorithms that's used for reinforcement learning. Then I can come in and say, okay, I want to configure this problem. If I'm just going to test it, I'll do 10 iterations. If not, I'll do 1,000 iterations. And then once I get to a certain number of time steps, I'll stop it. And then I can set up a scheduler, basically schedule a job to say that I want to go after this metric mean loss, and I want to try to minimize it, which means that I want to minimize the loss function in my pseudo machine learning algorithm. That's what you're usually doing. And then it's just a matter of calling Ray-Tune with my objective function, my model, and then my configuration and what kind of scheduler I'm going to use. And this cranks along. I just ran this on my laptop right before the talk. And so I've got, it's running through the status where it's showing every number of trials. It's going to come out and print out its status. So it's showing here that I've got two parameters I'm trying to search for. One is height and one is width. Those correspond to the height and width here. And what it's finding in just a few iterations is the width is pretty close to like 14. And so it's running through all these, and you'll see, I'll scroll through the log here. It would take a while, probably longer than we have, to run all these algorithms I was going to show tonight. So I'm just going to show the results. But basically, I'm running through all these experiments, and it's searching. And you can see, okay, great, we got a width 14, another one kind of okay with width 6, another one on and on. But basically, it's going through running a lot of parallel jobs and then finding out that, okay, my parameters for the width probably need to be somewhere around 14. So that hyperparameter is being optimized. You can see now it's kind of zeroing in. And I'll scroll down a lot further because this log was way too long. Let's get down to the bottom. But then we get down toward the bottom, and we've got something that's, at least for the width parameter, I ran it like 10 times, we're starting to zero in on it. And so then it would start to kick over and focus on the height parameter. It's like, okay, where can we zero in on that? And of course, if you have a lot of different parameters, this might take a lot of iterations. But there's an argument to be said that this is much smarter than just a grid search. It's much smarter than a brute force approach. And then typically, it's going to be much smarter than people who are just sort of throwing darts, who are, guessing about what the parameters should be. Or maybe guess, train a model, see how it works, go back and guess again. This is basically going to be a lot more efficient. So again, with really like less than 10 lines of Python code, let me drop this down. Yeah, with less than 10 lines of Python code for the part that did the training, I was able to go in and do some AutoML. I want to jump to a different set of notebooks here. Let me scoot this one over. Good. This is with a project in Python. It's called Lale, and it's a name in Persian. Half my family is from Iran and India, so I like seeing a Persian name on open source. It's called Lale, and it's basically doing a lot of what we were talking about in terms of meta learning. So Lale is a way to describe a machine learning workflow, a whole pipeline, and in ways start to synthesize parts of it. So here's an example using scikit-learn. And what we're going to do is we've got some sample data, and we're going to say, okay, well, at the first part, we might do some dimensional reduction using PCA, or we might just skip that. Maybe we don't need to. So there's two choices. There's a no-op or there's PCA. And then after that, okay, let's train a model. Let's see if we can use logistic regression or like a nearest neighbors classifier, and to see which one works out better. So we throw this in. We define basically a workflow here, really just a few lines of Python, and then we can visualize it. And so we've got these couple choice points, decision points there. Okay, now we go in and start to use Lale, start to build it out. And so it does some hyperparameter optimization. And we find out that, yeah, actually using PCA was good. And in this case, it was using nearest neighbor as opposed to using logistic regression. And this use case here, you can twist it two different ways. You can make it find the worst or make it find the best. But it's a real simple, concise example of where I have a data set, I have some possible algorithms that are known to be good with that kind of use case. Let me just throw together a workflow and let it solve itself. So I love what's going on with the Lale community because they're really integrating a lot of the other parts, and they're bringing in other open source projects and then making them work together. And I really love what's going on there. Now, this is another part that Lale has integrated. Just given the time, I can only show a couple, but it's called AIF 360 toolkit. It's the AI Fairness and Bias 360, and in this case, it started out at IBM Labs, but they were using work from Google and Amazon and others, Microsoft and whatnot, and then they contributed all of it to Linux Foundation. So it's an open source project at Linux Foundation now. But it's all about being able to detect bias in your training data sets. And that might lead to gender bias or racial bias or however. But how can we detect that even before we get in trouble and deploy the models? How can we catch it earlier in the workflow? And then how can we go back and rebalance the data that we have so that we're not injecting bias? We can work with unbalanced data sets, and we can algorithmically work with those. So in this case here, we're looking at, for instance, here's a credit assessment problem, and we've got some protected class data like what is your gender, what is your age. We don't want those going into the models. But even beyond just like what are the names of the columns, let's take a look at the data and start analyzing it to figure out where do we think that there is bias and how can we try to correct for it. So here, Lale is bringing in AIF 360, and then we're bringing in scikit-learn and XGBoost. So we're going to evaluate some different classifiers. And again, it's kind of the similar thing. We've got PCA versus not for cleaning up the data. And then our choices are logistic regression, XGBoost, very popular, or support vector machines. And that's all defined up here. It's just like a one-liner in Python. It's really great. Okay, so then we go through and we do some training. We find out, okay, for this data, it looks like PCA is good. And then we're going to go into logistic regression. But then we start looking at the metrics, and then we start to bring in, okay, let's reevaluate that in the context of how much bias has gone into this model. And can we define some privilege groups versus some, basically some columns that could introduce bias versus others that wouldn't. And we can come out with attributes to start to zero in on where people should look at the disparity that's coming out of how the model is trained. So I think that this is fascinating because now we can start to pull together, 5 or 6 different open source projects in Python and build a workflow and start to do the automated training. But along with it, let's not just look at how accurate it is. Let's look at how much disparity is going into it and really what's the impact on the judgments that's coming out of that. AIF 360 is like a universe into itself. There's a lot in there. I'm not going to go really be able to do it justice within a few minutes. But this is a real, concise example showing how one of the kinds of use cases for it. I could go a lot further. There is a article that goes in detail that, again, this talk was based off of, and that'll be in the links that we share. Kind of goes into more history and a little bit more discussion. There's a lot of links. One of my colleagues, So Upcar Litter, who does one of the developer meetups in San Francisco for IBM, he put together, based off of what we're doing in this talk, he put a lot of the links together into one GitHub project. So that's kind of one-stop shopping. And the slides are there too. There's a really great article about AF 360 being integrated with scikit-learn that's been pretty recent. So I'm excited about how that, I'm helping to build out some of the use cases and tutorials for it. The papers I was talking about, those are mostly on archive, but Show Your Work is a really, really great paper. And then this one is scary about like one machine learning model costing the same as running 5 cars during their lifetime. Really crazy stuff in terms of energy, and let's not destroy the planet by using AI. Awesome AutoML papers is here. I highly recommend what's going on there. Really great person to follow, Hadazian. And if you want to look more at Raytune, here's a tutorial that Dean Wampler and I did recently that there's actually a video for it, but it's taking market data for the last century and then running a multi-arm bandit in Ray and using Raytune to optimize it. And it actually comes out with like a 7% return on portfolio. It's pretty cool. The other thing that I'll throw out is I'm on the committee for JupyterCon. I was the chair for the last one 2 years ago. Joel Gruss, who spoke before me, he gave the best talk, the most popular talk about why he hates Jupyter Notebooks, and people, it was really, really excellent work. We hope to have a lot more coming up on October for that. And with that, I'll turn it back over. Thank you very much.
Awesome. Thanks so much, Paco. Can we give Paco a round of applause in the chat? So we do have some questions in, but if you do have a question, please ask them in the chat. I will be reading them out. So personally, do you see AutoML causing the field of data science to contract or expand going forward?
I actually see it being able to expand. I mean, I think, so Ben Lorica, my colleague Ben Lorica and I did this set of surveys a couple of years ago about AI adoption in industry, and it was really fascinating. It was supposed to go out to like 300 people after a conference, and the marketing person, there was an email list that had tens of thousands of people. Somebody hit the wrong button. So we got like all this data coming back about enterprise use of machine learning, and we started analyzing it. We did 2 other follow-up surveys to really dig in. And what Ben and I were finding, and what we're seeing now out of like the ML Ops community is, wow, there's a whole bunch of research and there's all kinds of amazing software to go in. But the time that it takes from like a business person describing a problem to like actually seeing some proof point of like, hey, can we write code that actually makes this work? You know, if that time goes beyond a certain limit, nobody cares. And so there's this real opportunity to use AI, and a lot of companies are really going for it. Other companies are like, why should I bother?
Yeah.
And you know, we see the split. It's about 56% of the companies that are kind of like, why should we bother? And it's a shame because, you know, you have to get your ducks in a row. You have to get your data infrastructure in shape, and you have to pay down tech debt, and you have to build up your teams and allow them to be able to collaborate with each other. And if you don't do those things, you won't be able to really take advantage of machine learning at an enterprise scale. And all of those things take years to really fix as far as enterprise transformation. So we see this sort of this split between haves and have-nots, where some companies get it and they're moving ahead and they're increasing their investment. And then others just don't care. They're not even getting started. They're already years behind. When Ben and I did the survey, we had this question about how much money are you spending out of your total IT budget on machine learning. And, you know, we were like 5, 10, 15%. And like, we did a catch-all 20%. It's like, nobody's going to choose that. It was like 40% of the companies that have deployed machine learning for 5 years or more are spending more than 20% of their total IT budget on machine learning.
Wow.
So there's this big split then between the haves and the have-nots. And it's really serious. And I don't think that, you know, AutoML is necessarily going to get rid of anybody in data science because there's so much demand. But what it's going to do is like the older, stodgier companies that are kind of late to the party, it's going to at least give them ways where they can go in and be more competitive. So in some ways, maybe it saves jobs.
Okay, that's awesome. So would you say it's like ready for prime time? Like, would you be running some of these models in production?
Yeah, there are some parts. I see some old friends on here. Hi, Paul. Yeah, there's some parts, and I would point to some of the companies, some of the vendors I listed there. I have friends. I'll shout out to my friends at Determined AI, Amit Talwalkar and Evan Sparks and company. They've been doing really excellent work. They just moved a lot of their stuff into open source, but yes, certainly production. A lot of the companies that are really active in deep learning, they're training on their own hardware. That's kind of what we see. For the people who are really into it, they buy up hardware. But then how do you optimize running on your own hardware? Determined AI has done some really interesting work. Amit Talwalkar was one of the early people, and Evan also doing their postdocs in AutoML kinds of areas. And so, I mean, this is like mainstream companies. How do they reduce the bill for training deep learning models? Because that can be a really serious bill. And there's other areas too. I think a lot of these open source projects are really interesting. Like Lale is sponsored by IBM, and IBM's doing AutoML, kind of the full end-to-end lifecycle. Some of the other providers are really looking at supporting that whole end-to-end lifecycle. Ibn Ilas, professor at Waterloo, is the one who did Holocene. Got to talk with him. Really fascinating work. I think they'll be commercializing that. I definitely think like Snorkel and some of the other areas of like data preparation, that's super valuable. So yeah, I mean, I think that AutoML is a big umbrella name, and certain pockets of it are ready for prime time. Others still need a lot of research, but they're evolving.
Mm-hmm. That's awesome. And yeah, shout out to Waterloo, my alma mater.
Oh, awesome. It's such an amazing, I mean, like when I worked at Databricks, it was crazy because like half the team had gone to Waterloo.
Yeah. It's a fun place. So I had a question. So you were talking about how the ideas from like the 80s are coming back in fashion now. And I sort of feel like that happens in software quite a bit. Like every 10, 15 years, like this conference talks, like the things Sandy Metz was saying about object-oriented Ruby, those same ideas are coming up in like Python right now. So are there any ideas you sort of see that have been like fallen off the popularity side that you think might come back?
Yes, thank you very much. Excellent question. So, I mean, I was around in AI, like I say, I'm old and gray. I was around back in the 80s, where there were people who were old and gray at the point in the 80s that were my mentors. And they were talking about things like scheduling and planning and machine learning. I mean, a funny story, but my graduate advisor was Doug Lennett, and he was one of the first professors at Stanford doing machine learning models, really, a lot of work in it. And they bounced him. Like they denied tenure because they said his work was too empirical. And like 10 years later, some of those same professors became billionaires by like investing in Google, right? So a little bit of a hypocrisy thing going. But the thing was that back in the 80s, the view was, machine learning is interesting, but it's a really small part of the problem. Like scheduling, getting robots to be smart about how they move in the real world, that's a hard problem. And now we're back at it. We have these issues of like self-driving cars and other drones and other things about robots not wanting to hurt people. And those are scheduling problems. And so they aren't machine learning problems in terms of supervised learning, but they can be addressed with things like reinforcement learning. And the interesting thing is like, you read the papers about reinforcement learning, a lot of it is optimal control theory. And I mean, that goes back decades. That goes back to like when, back in the 50s when aircraft were falling apart midair, when they learned how to build airframes in a more robust way and have control systems that, so that's really what we're going back to now. And so I do think that in particular, reinforcement learning is interesting for real world, especially like factory floor optimization, supply chain optimization. I also think the knowledge graph is coming back a lot because a lot of what supervised machine learning has done is to decontextualize a problem. Like we take a whole bunch of data and we train, we learn, we generalize, and we throw the data away. And so then we got this model and we don't really know why it's doing what it's doing. So now we've got a problem because we have to explain it to the auditors or, whatever. But the other thing is we've thrown away the context. And knowledge graph is sort of orthogonal to machine learning in that it provides context. And really, I was mentioning Lyft. A really great example is my friend Mark Grover is the product manager for an open source project called Amundsen at Lyft, which is sort of knowledge graph, their answer to GDPR, but it's in support of their machine learning work. And they found that like doing the right thing for GDPR actually led to a lot of performance increase inside their company. But they needed that knowledge graph to be able to augment it. They need to understand where does the data come from, where does it go to? So I see a lot of these kind of old school ideas coming back to the fore.
Yeah, one of my buddies just gave a talk, Hello Wayne, about if software engineers are really engineers. And like, I think a lot of these things that we're going to be solving, they're going to have to take the lessons from other fields and make software a little bit more, I guess, like a harder type of thing. Cause like, there's so many ways to solve a problem. And it's like, we need to standardize that in a way.
Well, I mean, I really think that like my favorite use case of machine learning is how can we make IDEs smarter? It's like I spend a lot of time writing code. I'm almost 60 and I write code every day. Like I spend a lot of time like looking up little nits in some weird GitHub repo and then tracing down a bunch of Stack Overflow questions and finding out like out of the 5 Stack Overflow questions, which one's actually valid and what answer still works from 10 years later. You know, that stuff, why do I have to do that? I could train models to do that.
Yeah. I think there is something on PyPI where it's like you can import Stack Overflow and like put something in and it like brings out like the top answer, which I think is amazing.
Right. Brilliant.
Yeah. Do you would you be able to provide links so we can share them out? Because like you had a lot of things to share.
Absolutely. I can follow a lot of that up. Most of the links of what I talked about, like I say, Upcar had this, and I'm gonna put this in the main chat. For today's talk. Cool. Okay, so I just put a link to a GitHub repo that one of our other meetup hosts had done. And he sort of, you know, he like pulled out all the links out of the talk and put them in one GitHub repo. So a lot of it is all right there. And also we're sharing the links, I mean, the slides, which have all the links in them. And there's a few repos that have different notebooks if you want to rerun some of the examples. Again, some of them might take like, 10, 20 minutes, depending on your laptop. So all of this stuff is meant to be really hands-on for everybody to go in and try themselves. The big list that I had is linked in the slides. It's that Google spreadsheet doc that I've shared, but that's live for anybody to go in and check out, and we'll keep curating that.
Awesome. Yeah, it's always great to have like resources that are constantly being updated. So thank you for providing these resources.
Awesome.
But before we do let you go, do you have any calls to action for our community?
Well, I will definitely say that, let me dig up one here. Definitely the IBM community. Let me go back to my slides here real quick. There's one last slide that I want to do as a call to action, and I'll share screen real quick. Entire screen, sure. And so this is current slide. Here's an offer. The IBM data science community, I really love what's going on there. There's a lot of people from all over the world, especially, it's not just the US. There's a lot of people from Europe and Asia and South America, et cetera. And so it's kind of one-stop shopping. If you have a problem and you want to compare notes with other people or get some good advice. There's also a thing where they partner with Coursera. So, if you join the community, you can get free credits on Coursera for taking courses there. Again, we're trying to have a lot of different kinds of presentations. AutoML is one that I've developed, but there's others in terms of ML ops and fairness and bias and a lot of the kind of hot topics that we see these days in data science. Will Roberts and I have been doing a lot of writing together. There's another article we just did about visualizing geospatial data in Python, so looking at GeoPandas and some other libraries that go along with that. So we try to throw in a lot of resources like this. So I highly recommend.
Awesome, and yeah, just a shout out to Tim at IBM for introducing us. It was a fantastic talk.
Awesome.
So thanks again for being on, and we'll see you around.
Thank you very much.